In this video, we'll discuss a little bit more about a function being continuous, right? So, okay, before we do that, let's have a very small extension of our the definition of being continuous. Definition. Like the left limit, right limit, and sometimes our function behave good on the right side of a number, we call that right continuous from right? So very natural way to extend being continuous, right? So f here is called continuous from right. And very similarly, you can define from left, right? Or left. And add a number a here, right? If what happens, if as x goes to a from right side, f of x equal to f of a, right? Nothing bad happens on the right side of a. And on left side for sure means the left limit as x goes to a on left side, f of x equal to f of a. So that's our definition of continuous from right or left. And because we will discuss what interval the function is continuous, right? If you have a closed interval at the endpoint, just either continuous from right or continuous from left, that means the function is continuous everywhere, right? And by our fundamental rules about evaluating limit, the following results are coming very naturally theorem, right? So if you have f g here, this is our assumption here. Though both of these functions are continuous at a, right? C here is a constant. Always see the constant is a number, right? This is our assumption. Then we can get lots of new functions. For example, f plus g and f minus g and c times f and f dot g product and the quotient we have f over g, right? But if you have a quotient, we have to make sure the denominator is not 0. So we are assuming g of a here is not equal to 0 in this case, right? All these functions are continuous at a, right? So this is basically easy. You can easily derive them by the definition of limit and also by the fundamental laws in evaluating limit, right? Because this two assumption means their limit exists as a finite number, which is either f of a or as x goes to a, g of x equal to g of a, right? G of a here. So if both limits exist, then there's some difference product quotient when the denominator is not equal to 0 or always exist to be f a plus f g of a or f of a minus g of a or c times f of a or f of a times g of a or f of a over g of a, right? This is basically from the definition here, right? Okay, now let's see a very natural observation, right, of the observation. right? So at what kind of point is not the function is not continuous, right? We have a graph in the previous video. This one just a small change, right? Suppose your function is something like this. Or sometimes you have vertical asymptote. So this is our vertical asymptote. But at vertical asymptote, you might still have a function value, right? So then you have the red. A function value is red. And so this is our another pros, right? So this function value is somewhere here, right? So this is our function y equal to f of x. So this includes all the possibilities, not all the possibilities, all the possible points in the domain, so which means f of a exists, which is not continuous, right? You can see that if the function is not continuous at a point A, right? And when A here is not in the, when A is in the domain, and if this happens, you have a hole, right? Or you have a gap, or you have a vertical asymptote. Then this function is not continuous, right? Something like this. And so let me write down that. So if the graph of f has no holes, right? The first one, or jumps, or horizontal asymptote on its domain, right? Then what happens is function must be continuous, right? Then f is continuous on its domain. Sometimes we write this as the domain of f, right? So we can consider all the elementary functions, recall all the graphs. We don't have any of this, right? So the fact here is based on this easy observation, y equal to sine of x, y equal to cosine of x, y equal to tangent of x. You might wonder, tangent x has a vertical asymptote, but the at that vertical asymptote, that x value is not in the domain, right? So only you have a vertical asymptote, and also the point is defined. I mean, f of that point is defined. Then the function is not continuous. And y equal to e to x, y equal to arc sine of x, y equal to arc tangent of x, y equal to natural log of x. All these functions are continuous on their domains, right? On their domains. So that's what we have here, right? And so, okay. So let's see another example, right? Another example here. What about compositions, right? Let's try to evaluate this function, the limit of this function, f of x equal to arc sine of square root x minus 1 over x minus 1, right? So let's see what's the limit of this function, right? We want to calculate the limit of x goes to 1, f of x, right? This contains arcsine function and also a quotient of some weird function, right? How do we do that, right? As x goes to 1, you can see that if you plug in 1, you get a 0 over 0 inside, because inside of arcsine, right? And you cannot plug in 0 directly, but we do know that this function, okay, we do know that y equal to arc sine of x. This is continuous on its domain, right? On -1 to 1, right? Everything happens inside -1 to 1 is good, right? So now we wonder where what's the limit of the inner function. So this obviously is a combination of two functions. What's the limit of this? What's the limit of x goes to 1, square root of x minus 1, x plus 1, x minus 1, sorry. What's the limit of this, right? If this happens be in the domain of our ultra function, all you want to do is plug that number into that, because the limit of because if this one goes to somewhere that's in the domain, so the function ultra function here is continuous on the domain. So all you want to do is plug in the limit, right? So what's this? This is basically this is for sure we want to use our second way to evaluate limit, which is try to eliminate the zero factor, which is x minus 1, right? So in this case, by our discussion before, we need to multiply by the conjugate. This is square root x minus 1. Conjugate is square root x plus 1, x minus 1, square root x plus 1. Why do we do this? Because it's impossible to factor x minus 1 on the numerator out, right? It's impossible. They don't even have x minus 1. It has square root x minus 1, right? And so if you try to do this, because we want to cancel it, you have to somehow generate such a factor on the numerator. What we do is get rid of square root, right? Square root of x. How do we do that? Conjugate helps, right? So this is as x goes to 1, x minus 1, x minus 1, square root x plus 1. So this is our common factor, which is our zero factor, will be canceled. So if now you can plug in 1, which is 1/2. So 1/2 is in here. The function is continuous in there. So which is good, right? So this is basically arc sine of as x goes to 1, square root x minus 1 over x minus 1. So because the inside function converges to a fixed point, this point is in the domain of the outer function. So this is basically arc sine of 1/2, right? This is pi over 6 if you know the unit circle, right? So this gives us a way to deal with combination of two functions. And if what g here is continuous at a, g is our inner function, right? And our outer function, arcsine function, f here is continuous at what? At g of a, right? Then what happens is f circle g, the combination, is also continuous at a, right? We know that f circle g of x is defined to be f of g of x, right? So this is basically just as we imagined. If you have two functions, both are very good, behave what we should behave. So this combination of these two functions also is very good.